Here we are, chapter 22 already. Where did the time go? I tell you. Well, it's true. The semester is almost over and it's all downhill. Negative free energy from here. You better believe it. Here we are in the week of April 18th. We're going to wrap up with some nice biochemistry in chapter 21, and then we start this chapter, electrophilic aromatic substitution. And you'll see its fantastic review. Then, moving on, we just take the second half of electrophilic aromatic substitution. Really, chapter 22 and chapter 23 are a lot like chapters 20 and 21. It's just kind of two chapters that probably should be one. They're so closely related, but they'll go by in a heartbeat. And then finally we wrap up with chapter 26, which is polymer chemistry, and that's a great topic not only for review, but to get you intrigued by polymers and interested in perhaps taking Ted Papenfuss's polymers course later on. It's a really good area of chemistry if you want to work in industry. So, then, before you know it, blink of an eye, we've got the final exam. The Monday of finals week. So, we'll be doing lots of review. Alright, what is this electrophilic aromatic substitution thing? Well, let's go backwards before we go forwards. It's about pi electron nucleophiles, which was practically the very first thing you learned about. Well, that's not quite so true. But it was way back when in 2301. Basically, we know that pi electrons are nucleophilic. We got this pi molecular orbital above and below the plane of the alkene, and they can be electron rich and go out and grab an electrophile just like we're showing here. But it's a really super weak weak nucleophile. It doesn't want to do that. So you have to have a super strong electrophile like HCl, H2SO4, a negative pKa acid. Okay, or a really good electrophile like, say, bromine. Well, aromatic rings are full of pi electrons. Can they be nucleophilic? Well, we've pretty much ignored them all year, but sure enough, they can if you induce them with a really strong electrophile. Why? Because, again, you're trying to make an incredibly high energy intermediate. All right? And this high energy intermediate is even more unstable than the high energy intermediate from an alkene because, shoot, when you take this pair of electrons and react them with an electrophile, you are destroying the aromaticity of that ring. So it doesn't want to happen, and that's why we've pretty much ignored it for the last 20 weeks or so. This is very nicely illustrated, in fact, in the reaction of an alkene with bromine back in 2301, actually back in 2311, OChem lab. You may remember that you synthesized cyclohexene from cyclohexanol, and to prove that you had made the alkene, you add that deep red-orange bromine color. And so here's that nice orangey bromine, and then when you add it to the alkene, the Br2 breaks into the two bromine atoms that end up trans across the double bond via, you will recall, the bromonium ion. Doing a little review here if you couldn't tell. So, backside attack on this bromonium ion intermediate gives you exclusively the trans stereochemistry. But when I drip that red-orange bromine into a solution into a beaker full of benzene, the red-orange color just sticks around. No reaction takes place. So there's a huge reactivity difference. To compensate for that, every electrophile we add in electrophilic aromatic substitution are activated somehow, which makes them strong enough to tempt the reluctant aromatic. Okay, so what is this mechanism of which we speak? Well, actually, it's review. Review, review, review. There's two parts. First part is basically activating that electrophile. So here's chlorine and some Gen Chem review. Oh my God. A Lewis acid, what the heck is that? Remember that a Lewis acid is an electron pair acceptor. That's all a Lewis acid is. It accepts an electron pair. So we're saying there's something about this aluminum trichloride that makes it want to accept a pair of electrons. Well, that's fine. We got electrons up the wazoo here. My chlorine looks like it has the measles there, but those are supposed to be 3 lone pairs on each chlorine atom. So what makes a Lewis acid out of an aluminum trichloride? Well, more review. Looking at our friendly periodic table, there's aluminum right there in group 13, which is telling you, of course, that it typically only has 3 bonds. And that is sensible because it's aluminum trichloride after all. The Vesper says it's going to be trigonal planar, and molecular orbital theory hybridization says it's going to be sp2, 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 and a leftover unhybridized empty p orbital, which some nice lone pairs on my chlorine can dump into to make, well, that's cool. I wonder how I managed to do that. To make that. So coordination of my chlorine with my Lewis acid gives me this complex, the aluminate anion and the Cl plus extremely strong chlorine electrophile. So I can activate chlorine, I can activate alkyl halides. So my really somewhat, again, middle of the road electrophile, say methyl chloride or something, can coordinate to the aluminum chloride, and that basically turns this into either a free carbocation or an almost carbocation. It definitely activates the electrophile. Heck, I can even do this with an acyl chloride. Now, we know acid chlorides are pretty darn reactive to begin with, but if I just coordinate my chlorine to the aluminum to get this crazy aluminate over there, I can then use the lone pair on my carbonyl to pop that chlorine off and make this guy super electrophilic. It is called an acylium ion, and we'll see that electrophile used quite a bit in electrophilic aromatic substitution. So, step number 1, some way of activating the electrophile. Then your super strong electrophile can add to the aromatic ring. And that's kind of the old-fashioned stuff because it's really the same thing as electrophilic addition. So electrophilic addition starts with addition of the electrophile across the double bond, and in so doing it makes a carbocation intermediate. That carbocation intermediate, though, we're going to see goes on to do substitution instead of addition. So what I want to point out at this stage is, just like electrophilic addition, it's at this stage that the regiochemistry is determined. Now, that's actually chapter 22, but this is just some foreshadowing, thinking about where does this chlorine add? Does it go this way or does it go that way? In other words, which carbon ends up getting the positive charge determines the regiochemistry. And of course, which carbon gets the positive charge is going to be determined by resonance. Okay. Also note here that, of course, the carbocation is highly unstable. So if I were to take my nucleophile, whatever nucleophile happens to be present in the reaction mixture, and add it here, well, as I've said before, then I've destroyed my aromaticity. But by instead doing an E1 reaction. What? An elimination reaction? Yeah, you betcha. So instead of my nucleophile acting like a nucleophile, it acts like a base. You will remember from an E1 that you remove the hydrogen beta to the carbocation, and then you generate your aromatic ring again. So I'm going to from a high energy carbocation intermediate in a very fast subsequent step to my very stable aromatic product. That is the sum total of EAS. Now I should point out that again, this will come into play when we look at regiochemistry. Resonance contributors play a role, but what we really have is a resonance hybrid intermediate where there's a delta positive on this carbon, and this carbon as indicated in the purple box. Okay, so that's everything you need to know mechanism-wise for the next two chapters. What are the electrophiles? Well, the usual list. A proton. Proton's really not of very much interest to us. Synthetically, I'm not going to replace a proton with a proton. That's kind of dumb. But if I can add an R plus, a carbocation, to my aromatic ring, I can alkylate the aromatic ring. So, in other words, I could take benzene and turn it into toluene. That's slick. How about adding X plus? Well, we know we need to make bromobenzene, right? We use bromobenzene all the time to make our Grignards. But how do I make bromobenzene to begin with? Well, I brominate benzene. How about, want to feel like blowing something up, perhaps? You need a little trinitrotoluene? Well, you need to put nitro groups on your aromatic ring. That's TNT. And you take toluene and treat it with, well, I probably shouldn't tell you this in any kind of detail. You can Google it if you need to. But please don't blow anything up. But anyhow, that's electrophilic aromatic substitution. How do I make the tosylate? How do I make tosyl groups? How do I make tosic acid? I sulfonate my aromatic ring. And the best one yet, we can now go from something like benzene or just about any aromatic you want to think about and put an ketone on it. Now, we know how to do that right now, but not in one swell foop, not in one step. Electrophilic aromatic substitution allows us to do this in one step. So, it's a big deal. There's a mishmash of other introductory points in Chapter 21. The most important point I want to make, though, is that this all is great review of mechanism and resonance contributors. So you'll really wear out your pencil doing a lot of mechanism and arrow pushing, electron pushing in this chapter. It's a great review in that it will drastically enhance the contents of our synthetic toolbox, which I'm sure will make you happy. This means more and more interesting synthesis problems. And by now you should be thinking, well, this is kind of a problem, because if electrophilic aromatic substitution is about this being a nucleophile and adding an electrophile, NH2 sure is not an electrophile. That's not gonna fly. So there are parts to this functionalization of aromatics that we have yet to learn, and that will come in the second chapter, chapter 22, chapter 23. I don't know, yeah, chapter 23. Furthermore, we have some manipulations of aromatic substituents that we need to do that we will learn about, which are very cool. So, for example, this is not a very healthy or green chemistry, but you can see that if I have an alkyl group on my aromatic ring, I can actually oxidize it up to the carboxylic acid. So a new oxidation reaction. We will see that, here's how I make those, how I put that nucleophilic NH2 group on my aromatic ring. I get there by a reduction. You can see that the nitro group is highly oxidized. Look at all those oxygens, replacing them with hydrogens. I got to learn some more reduction reactions. And then finally, cool beans. Somehow or other, I stick a nitrogen gas leaving group on my aromatic ring. That's pretty amazing. And you find out that, yes, it's true. I have been lying to you all along. You can do substitution on an aromatic ring. It's not straightforward though, just tell you, it's not a complete lie. Okay, so we wrap this chapter up. We wrap this mini lecture up with nomenclature, of course. You need to review your nomenclature. So that means looking at this molecule and telling me what it would be named. And this is obviously a Ferris wheel. Get it? A Ferris wheel? Yeah, that's a really bad, really old OChem joke. Okay, see you in class.